So this one I hope is fairly straightforward. There's a bunch of carboxylic acid syntheses. Most likely thing you're going to do wrong is not keeping track of the number of carbons. There are 6 carbons in this molecule, so there need to be 6 in the carboxylic acid. Most common mistake on that problem is losing this carbon and ending up with only a 5-carbon carboxylic acid. This one has 4 carbons. Same number of carbons, so that's just a simple oxidation. Over-oxidation in this case. Or you can use potassium dichromate in aqueous acid. You'll notice in this one we're adding a carbon. So that's a carbonation reaction. We're going to use CO2. So in the first step, we're going to make it greener by adding magnesium to ether. That will make phenylmagnesium bromide. And then we're going to react that with CO2, usually CO2 solid in the form of dry ice. And then we will work that up with aqueous acid. The product after the CO2 solid step is the magnesium salt of the carboxylic acid, carboxylate salt. So we need the aqueous acid work up to propane carboxylic acid. You could actually have done this a different way. It would have been possible, because that's a secondary bromide, you could have reacted this with KCN in a polar aqueous solvent like HMPA, for example, to make the nitrile. And then done exactly the same reaction that we had in step 1, where you hydrolyze that nitrile to the carboxylic acid. So that's also legitimate. It works not on tertiary bromides, obviously. If you have a tertiary bromide or a phenyl bromide, you can't do this. You have to do the carbonation. But in this case, since it's a secondary regular alkyl bromide sp3 hybridized carbon, you could add that carbon to it by doing this SN2 reaction with KCN. Get it the same way. This is the cleavage. Not that carbon. Right. So that is running KMNO4 under basic conditions. This one is an oxidative cleavage, so ozone dichloromethane followed by hydrogen peroxide to end up with the diacid. And again, we have to make sure we keep the right number of carbons. So we have 6 carbons in our product, 6 carbons in our starting material. This reaction is saponification. Converts the ester to the carboxylic acid, and we get methanol as another product. In this case, we don't care that we get methanol as another product, but we do get methanol as another product. And then this one is the Kolbe reaction. And that's going to put the carboxylic acid adjacent to the hydroxyl group. There's usually acidic workup in, like mild acid, something like ammonium chloride. So you had a choice of doing the mechanism for saponification or of doing the mechanism for the Kolbe reaction. I'm going to do both. Because they are somewhat different in terms of the class of reaction they fall into. Where saponification is a nucleophilic acyl substitution, and the Kolbe reaction is a nucleophilic acyl addition. And the saponification mechanism is one of the 3 standard ways to do a nucleophilic acyl substitution. And this is when we have a relatively unreactive acid derivative. And it's strongly basic reagent. So this mechanism for saponification is characteristic of all of the examples where we have relatively unreactive acid derivatives like esters and gametes. And we have strongly basic negatively charged nucleophiles like alkoxide ions or amide ions or things like that. And in all of those reactions, step one is attack of the nucleophile on the carbonyl carbon into a pi-star orbital. And when it donates back into that pi-star orbital, it breaks the pi bond. And forms a tetrahedral intermediate. This is the opposite of what goes on in an SN1 nucleophilic alkyl substitution, where we start with a tetrahedral molecule and we lose the leaving group to go planar. We have an sp2 hybridized intermediate. Here we start with the sp2 hybridized carbon and we end up with the sp3 hybridized intermediate. And then that can come back in and either kick out hydroxide to go back to the starting material or kick out the alkoxide. So it's pretty simple. It's nucleophilic addition in step one and elimination of the leaving group. In step two. And that's why another name for nucleophilic acyl substitution is acyl addition elimination. We have those successive steps where we're adding our nucleophile to the carbonyl carbon, and then we're eliminating the leaving group. So this mechanism only works if you have something attached to your carbonyl carbon that can act as a leaving group, which is why the carboxylic materials undergo nucleophilic acyl substitution, and carbonyl groups, where this is hydrogen or carbon, don't have a leaving group, they undergo nucleophilic acyl addition. The reaction is driven forward by an effectively irreversible proton transfer step has an equilibrium of about constant of about 10 to the 10th, because the carboxylic acid proton is much more acidic than the alcohol proton. So we end up with our carboxylate salt and methanol. And then in the acid step, the acid workup, protonate that with concentrated strong acid, or sorry, dilute strong acid, usually about 1 molar HCl to generate the carboxylic acid from the carboxylate. And again, that's got a high equilibrium constant, of about 10 to the 7th, so we show those two reactions as irreversible, because the pKa here is -2 versus 5, and on the other step, pKa here is 5 versus 15. So the first two steps are equilibrium, but we're driving those forward by irreversible proton transfer reactions. So there's 4 steps in this, 3 in the first part of the reaction, and that third step is a proton transfer. And that's actually common to most of the nucleophilic acyl substitution reactions where we have a negatively charged base and we drive the reaction forward by deprotonating the relatively acidic hydrogen. Right? So that's a standard mechanism. You can do it on the esters. You can also do it on amides. And the mechanism looks pretty much identical. The only difference is the leaving group. So if I actually do like base hydrolysis of an amide, and we started with unamide, for example. It's an unreactive acid derivative. It's a strongly basic reagent. The mechanism is going to look the same. We're going to go through the tetrahedral intermediate after nucleophilic attack. And then we're going to pick out the world's worst leaving group, NH2-. An absolutely terrible leaving group. Ammonia has a pKa of 35, which means the amide ion is an incredibly strong base. So this equilibrium is very unfavorable. And the only reason we can get that equilibrium to go at all is by driving it forward. Irreversibly forming ammonia in the third step. But it's the same mechanism. Nucleophilic addition in step 1, followed by elimination of the leaving group, followed by irreversible proton transfer. Who wants to tell me what the equilibrium constant for that reaction is? In order to do that, we need to know the pKa of the hydrogen of the carboxylic acid, which is around 5. And we need to know the pKa of the ammonia, which is around 35.
10 to the 30th.
So that's 30 orders of magnitude different, which means that the equilibrium constant is 10 to the 30th, right? For saponification of an ester, it was 10 to the 10th. There's no difference between 10 to the 10th and 10 to the 30th from the perspective of the reaction. They're both really fast, irreversible proton transfers. So that's a mechanism you should be pretty familiar with, where you can take an unreactive, which I mean an ester or an amide, carboxylic acid derivative, and treat it with strong base, and you can do this acyl addition elimination mechanism and come up with a product. You can make esters into amides using the same mechanism. If I were to treat this ester with sodium salt of methylamine, for example, in methylamine. And so I have the base and the conjugate acid. I could make an amide out of it. Pretty regular. Same type of mechanism where the base is going to attack the carbonyl group. We're going to go through an intermediate. It looks like this. And because we're in base, the intermediates are all either neutral or negatively charged. So neutral starting material, negatively charged tetrahedral intermediate here. And then we're going to kick out methoxide. Methoxide is a much better leaving group than CH3NH-. So in this case, that reaction is very favorable. And essentially not reversible. And then you probably wait until there's an acid workup, because methoxide ion is not going to deprotonate the CH3NH2, and it's not going to deprotonate this. Because it's not really an acidic proton. The pKa of that proton next to an anode is about 16-ish, which is comparable to the pKa of the ammonia. So there's going to be an equilibrium there, but it's not going to be an irreversible step. But you don't need an irreversible step in this case, because we're making this intermediate by taking out the much better unit. So again, it's a acyl addition of the nucleophilic anionic nucleophile followed by elimination. And it is always possible to go from a more reactive acid derivative, in this case ester, to a less reactive acid derivative, in this case gamete, under standard kind of basic conditions. Questions on that mechanism? That's one of the three fundamental ways that a nucleophilic acyl substitution goes. The basic reagent. And in fact, you don't have to have a unreactive acid derivative. The reactive acid derivatives will undergo that same reaction. So the mechanism for the Kolbe reaction is quite different, because it's more like enolate chemistry. The bicarbonate ion is a strong enough base to remove that acidic proton. I'm going to put this hydrogen in because that hydrogen is actually going to come into play. It's not there in the product, so eventually we need to remove that. So that's kind of an enolate ion. And then the other product is carbonic acid. So we've always got both bicarbonate and carbonic acid in solution. This is then going to attack the carbonyl group called CO2, kind of analogous to the allyl condensation. There are 6 steps in this mechanism, and all except for step 2 are proton transfer steps. So now we have a carboxylic ion. Can fairly readily be protonated by carbonic acid. Generate a neutral intermediate. And then the bicarbonate come in and take this hydrogen off the aromatic ring. Not really equilibrium. To regenerate the aromaticity. So that reaction is driven forward by the great stability of that aromatic ring, where you've got the 3 pi bonds adjacent to one another. And because the phenol is more basic than the carboxylate, we will do an intramolecular transfer here. It's a 6-membered ring intermediate. So if I redraw that, so that the OH group is pointing up, I think you can see that that's a 6-membered ring transition state. And when you have a 6-membered ring transition state like that, the transition state is aromatic. So that reaction is very favorable. Now I'm going to ask you what the equilibrium constant for this reaction is. Knowing that the pKa of the carboxylic acid is around 5, and the pKa of the phenol is around 10. If, granted, both of those are a little lower, the pKa of this is a little lower than 5, because of the electron withdrawing oxygen near it, and the pKa of this is a little lower than 10, due to the carboxylate group near it, but they're probably still about 5 orders of magnitude different, which means that that equilibrium constant is probably about 10 to the 5th. But now you can either use carbonic acid to coordinate that. I don't remember what the pKa of carbonic acid is. Or you can wait until there's an acid workup step. Generation of carboxylate. So it's a 6-step overall reaction with lots of proton transfers. You basically take the proton off here, and that proton is going to end up attached to the bicarbonate in the end. So that's not a nucleophilic acyl substitution, though. That's a nucleophilic acyl addition. We're adding our nucleophile to the carbonyl carbon, and then we're protonating the carbonyl oxygen. So steps 2 and 3 of this mechanism are nucleophilic acyl addition across the carbon dioxide. Right? Here's the nucleophile that attacked the carbon dioxide, and here's the hydrogen that added across. So we've added basically those elements of the phenol across it. And then everything else is a proton transfer step. So not a nucleophilic acyl substitution to all together. Questions? I'm going to save this recording